All right, gonna flip physics because I am again away this week and we didn't want to mess the schedule up for you. So take a look at the outline for today's notes. We're getting into chapter 4, Newton's second law. So take a second to write down the outline. I'll introduce Newton's second law. I'll talk a little bit about friction. Again, we'll talk about mass and weight, something we've talked about a lot. And then you have a worksheet to do in class. If you finish that worksheet in class, you can begin reading your book. If you don't like reading in class, you can begin working on test corrections because you should have your test back. All this homework is due on October 19th. That's Thursday. All right. So let's get going. First, Newton's second law. What Newton's second law states is that the acceleration of an object is directly proportional to the net force acting on the object, is in the direction of the net force, and inversely proportional to the mass of the object. Now that sounds really complicated, so I'm just going to show you the formula for it. The net force is directly proportional to the mass, and the mass is inversely proportional to the acceleration. This, I think, is the best way to think of Newton's second law. The net force acting on an object is equal to the mass of that object times its acceleration. The book will talk about it this way. The book will say the acceleration is directly proportional to the net force and inversely proportional to the mass. Hopefully you can see that solving this formula for the sum of the forces, or the net force, you would get MA. Some books talk about these formula pyramids. So if you get a formula like sum of the forces equals MA, the way you would do that is you'd put an M down here at the base and an A down here, and then you put the sum of the forces here. What that allows you to do is if you put your hand to cover up one of these things, you would get the formula for, you would solve for that. So if you want to solve for acceleration, cover this up, and you would get net force over mass. To solve for mass, cover this up, you get net force over acceleration. To solve for the net force, cover this up, and you get mass times acceleration. I don't care how you solve these, if you just want to solve them symbolically, but know the formula that I just kind of messed up by putting a box around it, but the sum of the forces equals mass times acceleration. I'll give that formula to you, but also when you read this, think of this as net force. The sum of the forces is the net force. All right. So how do we use that? How does that help us? Well, we talked about objects that were at a constant speed or that were at rest, objects that were not accelerating. And there we said the sum of the forces equaled 0. Well, one way to think about that is if we're at a rest or at a constant velocity, then acceleration is equal to 0. So if you were to plug that in here, you would get Newton's first law. So Newton's first law is consistent with Newton's second law, meaning that if we know acceleration is the rate at which something speeds up or slows down, if an object is not speeding up or slowing down, in other words, it's at a constant velocity, which could be that velocity of 0, then the sum of the forces is 0. But if it's not at a constant speed, if it's not at a rest, now we can deal with this formula and talk about, well, what are the forces acting on it? Let's take a look at an example problem. This is actually the first problem in your worksheet, so you may want to write this down. This is a top-down view, a bird's eye view of two people pushing on an object. that object, it says in the handout, is 100 kilograms. And it has it to 4 sig figs. Now, Bea is pushing this with a force of 85 newtons, and Alice is pushing this with a force of 100 newtons. And it should be pretty obvious that Alice is pushing this with a net force of 15 newtons to the right. 85 newtons is canceled out with 85 of these, leaving 15 in that direction. So that's the net force. That's the sum of the forces, thinking of this as a negative 85 and this as a positive 100. So we just found the net force. The other thing we know is that this object weighs 100 kilograms. That's a mass. Oh, I just totally misspoke, didn't I? This object does not weigh 100 kilograms. It weighs 1,000 newtons. This object has a mass of 100 kilograms. According to Newton's second law, the net force acting on an object is equal to the mass times the acceleration. Because we know 15 newtons is the net force, and we know the mass is 100 kilograms, we can now divide both sides by 100 kilograms and solve for the acceleration. Don't worry about sig figs right now. If we were to be worrying about sig figs, it would be 8. 8. I don't know where I got 8. It would be 2 sig figs. These two right here. We get A is equal to 0.15 meters per second squared. Now, one of the big mistakes kids will make at this point is they'll say, wait, Stubbs, you said the acceleration is always 9.8. It's always 9.8. Well, that's what that's what g is when we're talking about an up and down direction. This is a box moving left and right. That object, its acceleration is due to the forces that these two people are applying to it. Think about sliding a box across a floor. It's not going to accelerate at 9.8 meters per second squared necessarily. It would if you dropped that box off a cliff, but it would only accelerate in the horizontal direction depending on the net force and the mass of the object. I want to touch back on that formula. The sum of the forces, or the net force, is equal to mass times acceleration. Remember that if we measure force in newtons, mass in kilograms, and acceleration in meters per second squared. Remember that a newton is a kilogram times a meter per second squared, and that if you are going to use this formula, you need to make sure that your forces are in newtons, the mass is in kilograms, and the acceleration is in meters per second squared. Otherwise, none of the units will work out the way they're supposed to. A conversation we've had before, but worth having again, is to talk about friction. I copied this image from the book. That's why you see some copyright stuff here. If we were to zoom in at a microscopic or a closer level between these two blocks, we would see some rough surfaces. And those rough surfaces are the reason that we have friction. So friction opposes motion due to these rough surfaces between objects. Now, some things are really smooth, like ice. And if you go stand on ice, you'll slip around because there's less rough surface and less friction. But at a lower level, at a very close level, most of the objects or most of the surfaces that we're used to walking on and dealing with are rough. We actually wear shoes with big, obvious, rough tread to help us gain that friction so that we can push against the ground. Think about athletes who wear spikes or cleats so they can really get that friction and stop when they need to. I copied this footnote from the book in your reading because I thought it was so great. Even though it may not seem so yet, most of the concepts in physics are not that complicated, but friction is different. It is very complicated. The findings are empirical, meaning that we've gained all of this from experiments. And so our predictions on friction are also approximate. What you need to know is we talked about the two types of friction. I like static and dynamic, but the book calls it sliding. Static friction and sliding friction, or dynamic friction. Static friction is the friction of an object that is not in motion. Not in motion. Just like static equilibrium is an object not in motion. Sliding friction is the friction of an object in motion. Static friction is always greater than sliding friction. This will always be bigger. And there's a lot of evidence for that. It's pretty interesting, but we're not going to worry about it too much. Just know that it takes more to start an object in motion than it does to keep it in motion. We've talked about that. Hopefully that kind of makes intuitive sense, but it takes more to get an object moving from rest. We will not necessarily calculate friction. We will figure it out from free body diagrams. All right, or I'll give it to you. In some free body diagrams, I'll tell you this is friction. Let's talk about mass and weight in this demonstration in your book. That's a really great example between the difference of mass and weight. So mass is that amount of matter that an object has, or as your book defines it, it says that mass is, it says it there, the quantity of matter in an object. It's also the measure of inertia, or sluggishness, that an object exhibits in response to any effort made to start it, stop it, or change its state of motion in any way. Mass is quantity of matter. Mass is a measure of inertia. And weight is the force on an object due to gravity. Weight is the force acting on an object or upon an object due to gravity. So Newton's second law says the sum of the forces equals mass times acceleration. I gave you a formula before this test that said weight equals mass times gravity. If gravity is an acceleration, mass is mass. Do you see that weight is a net force? Weight is a force acting on you in that one direction. Now, usually we have a support force pushing back. So we get a lot of the sum of the forces equaling 0 because I'm not falling down. But if we were to do free fall, right, that idea that the only force acting on you would be the force of gravity, that would be this formula. This demonstration is a great example between the difference of mass and weight. If I pull on this string slowly, the string that is more likely to break is the top string. And the reason for that is this top string right now has the weight of the ball, this metal ball, plus the force I'm applying, while this string just has the force I'm applying. If I slowly pull, increasing my force a little bit at a time, pulling on this string, this will have more tension in it, and it will break first. But if I suddenly jerk this string real quick, the bottom string will break because the weight has more mass. This ball has more mass, and there's an inertia there that doesn't want it to move. I promise you that's the case, that this string will only break with a slow, steady pull, and this string will break with a certain jerk because of inertia. The mass here does not want to move. So when I jerk that string, it's more likely that this bottom string will break due to the sudden tension there and the lack of movement that this ball will want to have. It will want to stay at rest. But if I pull slowly, then this will break. I want to look at one last problem with Newton's second law before I set you loose to work on your worksheet and homework. Let's take a look here at an example problem that will be similar to the worksheet that you're dealing with. Imagine you have a 100 kilogram block here. So the mass is 100 kilograms. We'll do it to 3 sig figs. Again, this is the bird's eye view. We'll put Diego here pushing. We'll put Chai here pushing. And we'll just do with those two. So let's say Diego has a force. So the force from Diego, we will say, is equal to 150 newtons. And then let's say Chai is pushing up, or pushing this direction, and let's say Chai is pushing at 75 newtons. You're going to have to remember right triangle trigonometry to figure out the net force acting on this object. Remember, I like to add vectors head to tail. So Chai is pushing up and Diego's pushing to the right. I would think of that as Diego's push and then Chai's push, or I'd think of that as Chai's push and then Diego's push at the end of that. Either way, what you will see is this diagonal vector here. This diagonal vector here, which would be somewhere in here. Good, that's the net force. So we need to do a little right triangle trigonometry to figure out that net force. This right here was 150. This right here was 75. Doing that quickly with my calculator, 150 squared plus 75 squared, that's 28,125. I take the square root of that number, and I get that the vector here, the hypotenuse, would have a magnitude of 168 newtons. Now, if I was doing sig figs, this is 2 and this is 2, so my final answer, that's actually a little different because, anyway, we're fudging it. So if I was to do 2, I would say this is 170 newtons. But right now, I'm just going to stick with 168. So the net force acting on this object is actually at this direction here. And it's 168 newtons. Now I can come over here and I can use Newton's second law that says the sum of the forces equals mass times acceleration. I know the net force is 168 newtons. I know the mass of the object is 100 kilograms. I don't know the acceleration. I can divide both sides by 100, and I can get that the acceleration is 1.68 meters per second squared. I know I'm in meters per second squared because my mass is in kilograms and my force is in newtons. Good? If I wanted to know, because acceleration is a vector, if I wanted to know the direction of the acceleration, I'd need to find this angle. And I could find that with tangent and say the tangent of theta is equal to 75 over 150. And then I would take the inverse tangent of both sides. I would get theta is equal to the inverse tangent of 75 over 50, which is 1/2, I believe. And so when I take the inverse tangent of that, I end up getting that angle is about 27 degrees. Good. Again, 2 sig figs divided by 2 sig figs, 1/2. That would be 0.50 because of the 2 sig figs. And then your angle would be 27 degrees. And that would be 27 degrees here. That would be 27 degrees north of east, looking down on that. Okay. Be good for Miss Bosca. Work on your worksheet. Work on your notes. You'll have labs on Thursday, and I can't wait for a week from today, or even less than a week from today, Monday the 23rd, because I'm done traveling, I'm done with trainings, and I get to just be back in class with you guys. Have fun today. Be good. Peace.